Esta técnica, en ambos casos, contribuye técnicamente con la apuesta por la electromovilidad. El programa ha logrado coordinar la generar conciencia a las comunidades sobre la importancia de la de alrededor de 1/3 de las emisiones de dióxido de carbono, además de tener la tasa de motorización que más crece a nivel mundial. Por ello, la reducción de contaminantes climáticos de vida corta y de las emisiones de gases de efecto invernadero vienen siendo cada vez más urgente a nivel global. En ese contexto, el Programa Global de Cambio Climático y Medio Ambiente de la COSUDE impulsa el programa Clima y Aire Limpio en Ciudades de América Latina, Calac+, en coordinación y activa participación de instancias de los gobiernos de las 4 ciudades que lo integran. Calac+ fortalece las capacidades de los funcionarios para que a través de políticas y planes de descontaminación se fomente el cambio hacia buses y maquinaria de construcción bajos en emisiones, donde la energía renovable como la electricidad viene tomando cada vez más protagonismo. Calac+ persigue 3 resultados. Santiago de Chile es una ciudad que ha emprendido el camino a la descarbonización del transporte. Esto hace que su experiencia en electromovilidad tenga potencial. Esto hace que su experiencia en electromovilidad tenga potencial.
Morning, everybody. Welcome to the third day of the International Seminar, Electromobility for Latin America, which is being held under the Climate and Cleaner Project in Latin American Cities Plus, Calac+. Calac+ is the result of an international cooperation agreement signed in Chile by the Ministry of the Environment, the Agency for International Development Cooperation, AGCID, and the Swiss Embassy representing the Swiss Agency for Development and Cooperation. This seminar is organized by Swiss Contact and AGCID in collaboration with the Ministries of Environment, Energy, the Energy Center of the University of Chile, and the Swiss Embassy in Chile. All those who are following us, we remind you that we have simultaneous translation. At present, you can see on the screen how to connect to the simultaneous translation system so you can change channels. For instance, if you want to listen in Spanish, you should go to the Spanish room. And to listen in English, you should go to the English room, as can be seen on the screen. If you are connected from a PC, you must click on the link where it says interpretation, then select the language and mute the original audio. If you are connected from a mobile phone, you must press the three dots that appear in the lower right corner, as can be seen on the screen, where it says more. Click on that, and then click on language interpretation, select the language that you wish, and mute the original audio. If at any time you wish to change languages, just enter interpretation and choose the other language. I hope that this was clear to you, but please remember that in the three dots under more, you can select the language you wish. This event has been held on the 25th, 26th, and 27th of November, and it is broadcasted for all those who have registered through the Zoom platform, both in Spanish and English, and also through the Facebook of the Calac Plus program. You can see the streaming live. Each day will focus on a specific topic. Today we will focus on electric fleet management. Yesterday we discussed financing. To begin with our third day and talk about electric fleet management, we will start with today's seminar on electromobility for Latin America, and we are going to start with a presentation of Juan Pablo Romero and Paulina Ramirez del Barrio. Let me introduce Juan Pablo. Juan Pablo Romero is a civil mechanical engineer from the University of Chile, a data scientist, and a master's student in engineering sciences. He has dedicated the last 3 years to research and study of energy, ecological, and economic efficiency of diverse technological projects, always focusing on the implementation of the most advanced technologies that help expand the frontiers of knowledge. He currently specializes in the use of artificial intelligence to solve both industrial and academic problems. Likewise, our moderator, Paulina Ramirez del Barrio, is a civil electrical engineer from the University of Chile. She is also a researcher in electromobility at the Energy Center of the Faculty of Physical and Mathematical Sciences of the University of Chile. And to add to this, she is a construction manager of PMGD photovoltaic projects in the CVE group and chair of the Association of Energy Engineers, AEE Chile. For those of you who are watching us, you can write your questions in the question section of the Zoom or through the Facebook of the Calac Plus program. You can choose any of those two platforms. So now we are going to start. Let me give the floor to Paulina Ramirez del Barrio. You can choose any of those two platforms. So now we are going to... Thank you very much, Beatriz. Good morning, everybody. We are going to present with Juan Carlos a study financed by Calac Plus and Swiss Contact, which is the methodology for the life cycle assessment of vaccines with the assistance of artificial intelligence algorithms. Let me see if this is working or not. This is taking place in the current context where, in Chile, transport is responsible for 25% of all the greenhouse gas emissions and almost 1/3 of the generation of fine particulate matter. This is due mainly to the main fuel that is used, which is fossil fuel. So Chile has set decarbonization goals by 2040, which is 100% of electric public transport. So under this context, we are developing, or actually, this assessment or study has already been developed, as you will see on the screen, with the goal of evaluating and verifying that electromobility is the way forward towards decarbonization of transport here in Chile. So this is both an economic and environmental motivation, because we want to reduce greenhouse emissions generated by public transport vehicles. And it's an economic motivation because we also wish to financially endorse this option. This is the most that it is worth investing in electric vehicles instead of diesel vehicles for transport. So at present, as pointed out in the previous sessions, we have a tender where we have Euro 6 vehicles and we have electric vehicles. In this study, we are particularly considering Euro 6 vehicles to make a comparison. Remember that Euro 6 vehicles are ecologic vehicles, green vehicles, because they have 1/100th of the emissions that old diesel vehicles used to have. So the key motivation is to improve the quality of air, ambient air, and also the quality of life that are using this type of transport. So we have a number of questions here in the presentation. Does it allow to reduce emissions? Is it more profitable to have a diesel than an electric bus? Is it more efficient? Does it allow to reduce emissions? Is it more profitable to have a diesel than an electric bus? Is it more efficient? So under this context, we are trying to compare the environmental and economic characteristics of these technologies, the electric buses that we currently have in the public transport system with the Euro 6 diesel buses. This is based on the data that are part of the study of the Energy Center, the Ministry of Energy, and the Ministry of the Environment, with the support of the Ministry of Transport and Telecommunications of Chile. So this study, which was presented in Williams Calderon in the first day of the seminar, considers data collection in the current system. So with all this data from the metropolitan region, we can build a total cost curve of ownership, total ownership cost, so we can economically compare the electric vehicles with the diesel vehicles. So on the right corner, you can see a study that was conducted in the UK in 2018, where they made this comparison based on the total cost. But this cost are the environmental costs as well of this type of technologies. For this, you need to do a life cycle assessment of this technology. So with this objective, we define this methodology, the work methodology that allows us to make this final comparison. This comparison allows us to model the lifetime of the technologies, the LCA from year 0 to the end of the lifetime. The lifetime of this vehicle, please remember what they said. It was 14 years. The lifetime of this vehicle, please remember the life cycle analysis from manufacturing of the vehicle to the end of its use. The life cycle analysis from manufacturing of so we are estimating, according to the study, through surveys and literature data, the phase of manufacturing and lifetime, and this is information available. Literature data, but we also use the data from the Energy Center of the University of Chile. And also, Juan Pablo proposed to use artificial intelligence, the state of charge of electric vehicles, and in this way, we can better define energy consumption during the phase of use of this life cycle assessment. Energy consumption during the phase of use. And in this way, you can calculate the emissions generated during that period, generated by that electric vehicle, so we can compare it with the emissions generated by a combustion vehicle. So we can do this with the emissions generated by a combustion. So as I said, with this total calculation of emissions of both CO2 and fine particulate matter, PM2.5, you can calculate the total cost using that formula. So how can we obtain this? I have to click on another link to move forward. So it is with a permanent life cycle assessment and with the total analysis of the cost. So now I would like to give the floor to Juan Pablo Romero, my colleague in this development. He is also the project lead, so he can tell you more about the life cycle assessment and the development of the results that were obtained from this particular study. Juan Carlos, please, you have the floor. Thank you, Paulina. Good morning, everybody. Juan Carlos, please, you have the floor. The life cycle assessment is a methodology that uses quantification of energy flows to obtain the environmental impact of an asset during its lifetime. As you can see on the image on the right, these phases, and as indicated by my friend Paulina, these phases go from the extraction of materials to the recycling or end of the lifetime. Sorry, I cannot hear him. In the case of electric buses, we distinguish these three phases, which is the extraction and manufacturing, where they manufacture the diesel engine, the electric engine, the batteries, the phase of use, where we have the operation of the diesel bus, the operation of the electric bus, and the maintenance, and the end of the lifetime, which is where we have the recycling of the components and the final disposal. So if we were to look at a closer look at the manufacturing phase, what we are going to have is the composition of the electric or diesel vehicle through a maximum percentage, and this we can apply to an environmental impact. In this case, on this table, we can see the basic percentage of the part of an electric and diesel bus. This is the same in both cases, and this we can apply to amount of CO2 per kilometers traveled. Let me look at the use phase. So in this phase, what we do is to model the energy matrix that Chile currently has. So in this way, we can obtain the environmental impact that the use of 1 electric megajoule by an electric bus coming from the energy grid that Chile has. In this case, in this chart, you can see the generation of CO2 by joule occupied depending on the source. In this case, it is for the current grid that Chile has, seen in a static manner.
In this case, we consider the matrix with a generation that is 100% renewable, which matches the contracts that electromobility currently has. Paulina might be able to tell you a little bit more about it at the end of the presentation. Lastly, the final phase, which is the end of the life cycle, we consider that 95% of electric buses or diesel buses, which are recyclable, the remaining 5% will go to the final disposal. With that, we will calculate the environmental impact of using this strategy. And in addition to that, we calculate within the economic analysis the second lifetime that the materials will have. In this graph, we can see a comparison between the diesel bus and the electric bus and the final phase, which is the end of its lifetime. Negative, it's negative generation, because when we recycle a material, what we do is we prevent that material to leave the and we remanufacture it, so it always generates a lot more emissions. So if you have to subtract the recycling, and then you have to calculate the emissions by extraction, and it gives you a negative. So the results, the general results, now if we take a look at the general results of the life cycle analysis for the current energy matrix or energy grid, if we take a look at it in a static way, maybe electric buses are not as good, but that's a static case. Now, if we take a look at the current case, the real case, we can see that if we take a look at the yellow box at the right that shows the fine particulate material, as a matter of fact, electric buses show that in the worst case scenario, they're a lot better to decontaminate cities from the point of view of fine particulate material. Taking a look at the yellow box. Now, if we consider taking a look at the yellow box. Now, if we consider the contracts that are 100% renewable that have been signed, we can see the actual potential that electromobility has. Because the difference, as you can see, in generation is very, very, very large, specifically in the usage phase. Manufacture, of course, since it has more electronic components, it's always going to be a little bit less clean, but it is compensated or offset largely by the usage phase. And the same thing happens with the generation of fine particulate material. So, we have these environmental indicators that we estimate with the life cycle analysis, and that is something that we have to transform into costs to be able to compare it against the operation maintenance costs, energy costs, the initial costs of the project that Paulina has explained. And here we have the TCO formula. And for that, we use the eco-cost that would allow us to transform the environmental impact into money or monetary value. And when doing that, we discover that, as a matter of fact, electric buses are, from the economic point of view, a lot more competitive than diesel buses, considering all of these variables that go from the cost themselves up to emissions. If we consider now that the projections that it has and the price of the materials that is exponentially going down, and if you consider as well that the contracts of 100% renewables that we have are complied with, then the difference would be a lot larger for electric buses. So, in a nutshell, as a conclusion of the study, we can say that because of its low operational and maintenance costs, the electric bus technology, from the economic standpoint, has a very important advantage if you compare it against Euro 6 technology. And because of the dependency that this technology has to the energy matrix, it has a huge potential to contribute to the reduction of greenhouse effect gases in large cities, and specifically in the decontamination of fine particulate material in cities, and that has a direct understanding that in this country they have checked these technologies, but we also showed in the presentation the study made in England. So why are the results so different when comparing the electric diesel technologies from one country to the other? Well, it depends a lot on the public policies of every country and the energy grid. For example, you were able to see that if we took the static energy matrix or energy grid, the result would be another. But we have a contract that says that we are going to feed electromobility with 100% renewable energy. That makes the study change. So it depends a lot on the conditions of a given country that you use to feed electric buses. And in addition to that, there are environmental conditions that make buses more efficient in certain areas and not in others. Here in Santiago, and I'm sure that Williams talked about it, Professor Williams Calderon, they're very efficient, electric buses, I mean. Perfect. Yesterday, in the Q&A session with the representative of the brands and the distributors, they talked about electric buses in regions. So as you said, in Santiago, conditions are good to be able to have a good efficiency. So can maybe this study be extrapolated to the regions, thinking that you would obtain the same result or not? The methodology of the study and the algorithms that were developed, yes, but I wouldn't dare to extrapolate conclusions to another region. Perfect. What is innovative about this study and your main input regarding artificial intelligence usage to manage large amount of data? A question from the audience is it costly to use artificial intelligence to assess energy efficiency, and is the system available? No, it's not expensive. I used models using, how do you call them? The word is not technology, the word is resources for everybody, right? Specifically, Google Colab, which is for free. Now, whether it's available, not right now, but with Paulina, we're going to release a paper, and when the paper is published, we're going to have a kit with the repository with all of the algorithms, and it will be made public. Perfect. There is another question around here about the assessment system. Does it allow to identify energy gains with the regeneration braking system? What assessment system are you referring to? Maybe I am the one who should answer this question, if you agree, Juan Pablo. Well, when we assess, using artificial intelligence, we assess the energy consumption. I think that that's the assessment that they were referring to. So clearly, there you have artificial intelligence to estimate the charging state, which considers how is the battery at that moment regarding its charge level. So the state of the charge considers the variations on the battery, whether this has to do with the consumption or the energy gain and the regeneration. So definitely regenerative braking is considered in this study because real data from the charging state has been considered for the buses. So I hope I had answered the question. I don't know if you want to add on to that, Juan Pablo, regarding the SOC. Well, basically, we use neural networks. And what it does is to imitate the behavior of human learning. And what we did with Paulina was to give the network the history of the charging state. So quote unquote, the algorithm knows how the SOC evolves due to the regeneration breaks in a specific window of time, and it knows also how the person is driving. So it for a very short time estimate is very precise. Of course, if you want to estimate a longer period of time, it's less precise. But for example, for 10 minutes of driving, it is very reliable. Very well, thank you very much, Juan Pablo. And there is another question here regarding TCO. What costs of carbon were assumed in the study? Do you have that piece of information at hand? I do. Let me see if I can find it. Well, while you're looking for that data, I just wanted to say that all of the values of the carbon cost were obtained from international. Well, while you're looking for that data, I just wanted to say that all of the values of the carbon cost were obtained from international. Well, while you're looking for that data, I just wanted to say that all of the values of the carbon cost were obtained from international. Thank you very much, Juan Paulo. So in case I wanted to replicate this study in other cities or other countries of Latin America, what recommendations would you give? Well, the study from us, as you know, has all of the tables of the life cycle analysis, and they are disaggregated, they are unbundled. So there is a lot of information to build the study from scratch. The other recommendation is that if you don't want to do that, you can pay for a license of CABI or Equinvent because they carried out the study with that database, but they are not free. So one of the good things about this study, and we have made a lot of efforts for the information to be totally available and for it to be able to be replicated totally. Thank you so much. And we have made a lot of efforts for the information to be totally available. We have no more questions. And I wanted to tell all of the people who are listening to us that this study will be available at Calac website. And if you have another question regarding the study, you can contact us through Calac Plus. So back to you, Beatriz. Thank you so much, Juan Pablo. You have the floor, Beatriz. Regarding the study, you can contact us through Calac Plus. So back to you, Beatriz. Thank you so much, Juan Pablo. You have the floor, Beatriz. Sorry, my microphone was muted. Well, things that happen in virtual seminars. So we will continue with the event. I would like to thank Juan Pablo very much for his presentation and also Paulina for leading the Q&A session. Now we will have another presentation. We will have Christian Martin with us. He's an electrical civil engineering, graduated from the University of Chile. He's an expert in power electronics. And he has 17 years of experience as a research and development engineer. And he's also a product marketing specialist, business manager, and he's also responsible for electromobility, ATV Chile, and he carries out projects of charging infrastructure for 5 years in the local market, together with the main segment stakeholders. And he also participates actively in the technical roundtables of the Ministry of Energy and in the roundtable for electric decontamination for electromobility. So thank you so much, Christian Martin, for being with us. Hello, Beatriz. How are you? Good morning. Can you hear me? So thank you so much, Chris and Martin, for being with us. That's good. First of all, I wanted to thank you for the invitation. I'm happy to be part of this seminar and to contribute a little bit of the developments that have happened and how electromobility is taking place in fleet systems both worldwide and at the local level. So I just wanted to say thank you so much for the invitation. Taking place in fleet systems both worldwide and at the local level. So I just wanted to say today, thank you so much for the invitation. We will address four main topics that have to do with some development examples, both for the deposit charging and the en route charging. And we will see the evolution regarding the development of terminals, regarding incorporating new technologies and moving forward towards new trends and the new revolution of electromobility globally. So I would like to show the depot charging and then Panto charging with energy management considering interoperability amongst the current systems and the buses in this case, to continue with autonomous driving systems that are already present in the market and they are a reality as well, and to continue with a topic that is extremely relevant and it has to do with the previous presentation, which is energy management and the cost ownership, total cost ownership that finally makes the electromobility profitable, and it gives a competitive advantage. Of course, you compare it to internal combustion. The electromobility profitable, and it gives a competitive advantage. Of course, you compare it to internal combustion. In a general way, for those of you who are not familiar with ABB, ABB is a global company. In Chile, at least, we've been here for over 60 years. We're in more than 100 countries worldwide. From the electromobility point of view, more than 14,000 units of fast charging sold worldwide, and we participate actively in all of the committees and congress associated to electromobility as a relevant stakeholder. And we are really proud of that action. We are the sponsors of Formula B, and we have best projects globally with more than 5 years of operation. So based on that experience, we will be showing you today information related to this technological developments. It is important to mention that for electromobility, we need to join different manufacturers of technology globally and partners. So here in this slide, I show some of the manufacturers that we're working with, both from European origin and Asian origin. And we have made important developments both in terms of consultancy, charging, and this is for the charging systems to be comfortable before beginning. For example, we need to take into account air conditioning, the driver. And that is fundamental in the previous charging phase. From the point of view of ABB, we have the entire package associated to electromobility, not only the chargers. but the comprehensive system of connection to the network, energy storage, control system, energy management, all of that is part of our portfolio. So in ABB, you can find everything, the entire package that you need to have your terminal put together. So that is part of what we offer today. Now, speaking of the subject matter of today's seminar, because we want to show you the progress made in technological development, the first example of application in this case has to do with the Netherlands, a fleet of 99 buses with the operator called QBus, and taking the commitment that the Netherlands has to reduce emissions to 95% by 2050. So that's part of the developments that were implemented here. And that is interesting about this system. What is interesting about this system is that it incorporates two different concessions. In one of them, there are 62 charge points of 100 kilos. In another one, there are 38 charging points, but among the routes, there are also panto systems. So that information is extremely important because in many cases, the panto systems that exist, we're afraid of not having battery along the way. So what happens here? There are chargers both in the bus terminal that are plug-in chargers like depot boxes, and there are also panto route chargers. So when the bus transits or it moves, you can charge in around 3 to 6 minutes. Well, it depends on the bus. So we have to remove the myths because people say that a panto bus cannot be charged in depots through a hose. No, you can do that as well. So here there is an invitation to have a charging mix in the charging infrastructure where in the terminals you can have depot type chargers, and en route you can have panto type chargers for this type of technology and for this type of buses as well. Moving forward with the developments, and now speaking of panto systems or pantographic systems themselves, this case is with BYD buses in Germany. This is a very interesting case where in the terminal there are around 20 pantographic units, panto up, when the pantograph is in the bus and it goes up to make the connection towards the electric terminal, and there are 3 chargers of 450 kilowatts en route to do the management of this type of buses. Why? Because precisely the battery, the size of the batteries of this type of buses regarding its autonomy is a lot lower. We are speaking of 20, 30 kilometers of autonomy compared to the plug-in buses that could have an autonomy of around 200 kilometers approximately. In this case, the solution, besides being pantographic, it includes a system to manage the fleet and energy management as well, and the benefits are a saving of 18,000 tons of CO2 in 20 years of operation. Here we will add another variable to innovation and technological development that has to do with a project in Canada where there are pantographic charging systems again. In this case, also pantographic as well, but this is down. And so the pantograph is in the infrastructure and it goes down to the bus. So why is this project special? Because it's been thought also for autonomous charging. So why is if without the need of having a driver in the vehicle. What are the challenges in this case? First of all, an issue regarding space. If you can take a look at this slide, the pantographs are located one very close to the other. So that is a very interesting challenge from the point of view of parity of the bus towards the pantograph connection. Because, as I said before, there is not necessarily a driver in the bus, and certain identifications and authentications are required for this to be made automatic. So a redundant authorization system was made so that the bus would detect the right pantograph for it. Another project also of similar characteristics, this is a pilot project that was developed with Volvo, and it precisely has to do with autonomous driving. So once it gets to the terminal of the bus, but what happens here? The bus gets to the terminal, the driver gets out of the bus, and the bus can autonomously continue to move forward to the final parking place, going through a driving or a charging spot before parking. So that's precisely where electromobility is going to, beyond fast or ultra fast charging points. This is a way to look at the future in terms of an autonomous system. This is a project in which, well, today we had very interesting news precisely regarding this project. This is a project in Italy, in Milan, where dual charging points are incorporated, equipment of 120 kilos that could charge two buses simultaneously. So here there was a problem related to space. So with this type of technology, the space was not a problem finally, and there were around 15% of space savings while building on this charging infrastructure. What is the innovation here? That here energy storage systems are used. A BESS system, BESS system, in addition to the charging infrastructure, and connecting it all precisely to control systems. Control systems on site called EVSS, which is a control to incorporate the charging infrastructure and the storage system and the electrical network itself that you have within your ecosystem, and we can call it the electric terminal. So what I will show you next is why do we have good news? Well, because today we have been notified that the complete system is operational, and in the control system, all of the storage system has been built into together with the infrastructure systems that are associated to it. Therefore, that means that there is a sound and single ecosystem in Milan for the development that we have carried out. The last example is an example in Hamburg, in Germany as well, where there are sequential chargers that are similar to the chargers that we have used here in Santiago de Chile with Redbus. And buses Kinglong, well, in this case, it's another brand of buses, and also an innovative system in terms of space, because the implementation of the charging points, different from the previous cases, is at the roof. So there is a collapsible system, and the connection cables go down to each one of the buses. And the benefit is of around 83,000 tons of CO2 savings in this example. Why is it innovative? because since it's an existing terminal, in this example, it couldn't expand more in terms of its size, and therefore a second floor system was developed where the electric room is precisely to give energy to the terminal. So there were no additional requirements related to the space in the development of the terminal, but it grew one way or another because the infrastructure is at the roof or ceiling of the terminal. So this is how, in these examples that I have just mentioned, I have been showing you different characteristics associated and development associated to electromobility. And it is here where I want to show you how these systems have been evolving regarding fleet development. And this has to do with the demands of the final customer for electromobility. The first phase is a phase that is relatively simple, where we had the chargers and basically light vehicles to generate the charge. So what did we have to do? A happy flow, a flow of energy between the charger and the vehicle. Logically, it has some challenges regarding interoperability and everything that has to do with the different brands that get into the market. But this is a first approach of doing an electric charge. Then, after this challenge, we have incorporated other types of vehicles. We are talking about trucks or buses into the charging systems so that they wouldn't only be able to charge light vehicles, but also heavy vehicles associated to the fleet. So logically, this was the critical point of the connection of these systems that are different, and we have to make them interoperable. Nonetheless, the demands have been growing, and here, from the point of view of the electric grid, from the point of view of the electric grid, so that the bus won't trip. And there have been limitations regarding the energy requirements, and that can be achieved through the communication system or CDP, which is very well known in general. But now we're also implementing a system that is a lot more industrial, which is OPC, that does not only include the management of chargers, but as I will show you, it incorporates other electric devices from the industry, from the terminal, or from whatever.
We are now at the stage where they are demanding to do peak shaving, which is basically to shave some peaks with battery storage systems. So we are requiring the control systems to include it as part of their development and responsibility. Likewise, the terminals and the industry at large to not only have a charging infrastructure or a VES system, but also generation sources, corporate buildings that need to be incorporated and managed as a whole. That is why we always talk about an electromobility associated ecosystem. So it is part of what is being required by the marketplace, and it is part of what we are offering. We as ABB, we want to be responsible for on-site management. Finally, to achieve this ecosystem, we need to have a coexistence of this electric infrastructure with the area of service associated to it, the fleet, schedules, issues related to energy as to the energy costs, and perhaps bi-directional B2G systems, which is vehicle to the grid systems, so we can incorporate them in a future stage, So the vehicle itself is part of this storage system, and in this way we can have some power shavings. This can be done through EBSS system, which is a system of control, an optimized control system for fleet systems and for the industry at large. To finish with my presentation, the last two slides I have left shows an example where a system where they did not incorporate a control system. And as indicated here, to make things more simple, we are considering 10 300-watt buses with 10 chargers of 100 kilowatts. So whenever there's no system nor management associated to the charging points, evidently the projects are not going to work well due to a number of reasons. First of all, due to an overcharge of the energy requirement, in addition to the, irrespective of the capacity I have in my electrical grid, I might be exceeding the limits of my electrical grid, and this might result in a greater capex expenditure by having to increase my substation. The other point is that in any project, in addition to having an electrical power capacity, we have to define a consumption peak or a maximum consumption target that is much below that electrical grid or power grid. As you know, energy is paid both by power, the invoice comes through power and energy, so the installed power can have a significant variation, and the costs are going to be impacted if your system, let's say that it's a 1 mega system, but you are going to use much less, or the other way around, if you have an excess in the energy consumed. So this first example clearly shows possibilities of exceeding both the electrical network or grid, which might create a trip in the system. The system might trip and collapse or to exceed the target. And this can have a strong impact on the project. In some cases, this could account for $35,000 in additional costs for the project. Nobody wants to accrue those type of costs. With an energy system, with a control system, what I can achieve here is to control those peaks of load, those load peaks, so it will never exceed the capacity of the grid or the proposed target as a company, as an energy consumption company. And in this way, I can have some capex savings in terms of the size of the substation. It depends largely on the facility, but it's around $80,000 on average in terms of the initial investment saving. And from the operational standpoint, around $19,000 of annual savings from the standpoint of energy management. So in this way, this gives us a cost reduction of around 44%. So by incorporating an energy management system, you will have savings, operational savings, with a very rapid return on your investment. Well, this is basically what I wanted to share with you. This is the evolution of the electromobility industry, how this industry has evolved over the last few years at a very fast pace. We see that from one year to the other, the requirements are much more stringent for us as infrastructure manufacturers. And the challenges are quite interesting ahead of us because our clients can have a rapid or quick return on their investment. So hopefully you enjoyed the presentation. I wanted to show you real-life examples of the development and the progress we have made around electromobility. I wanted to show you real-life examples of the developments and the progress we have made around electromobility. Thank you very much for Christian's presentation. Any questions related to this presentation? Who is an electrical civil engineer? For Christian's presentation. Sorry, she is breaking up. Who is an electrical civil engineer? Sorry, she is breaking up. Sorry, she's breaking up. Moving on with our presentations, we will hear from Diego Muñoz. Diego is a civil industrial engineer from the University of Chile and master in operations management from the same university. Both degrees were obtained with the top distinction. So please ask Diego many questions. He has 10 years of work experience in the public transport system of Santiago de Chile called Red Metropolitana de Movilidad or Metropolitan Mobility Network. Since 2014, he has been leading the operations and studies area of STP Santiago, where he has developed and implemented optimization models for fleet programming, both diesel and electric buses, and drivers, management control models, and fleet and electric bus charging management system. He is currently a member of the counterpart team before the operations, planning, oversight, regulation, and corporate finance areas of the Metropolitan Public Transport Board. So as you can see, he has a broad experience, Mr. Diego Muñoz, who is coming next. So I hope you take full advantage of his presentation. Please, Diego, go ahead. Mr. Diego Muñoz, who is coming next. So I hope you take full advantage of his presentation. Please, Diego, go ahead. Thank you very much for inviting me to take part of this seminar. I am going to talk about designing an electro-terminal and its operation. Thank you very much for inviting me to take part of this seminar. STP Santiago is a company with Chilean equity that has been operating in the red system since 2005. He is present in 30 villages, and it affects 50 million kilometers per year. We are distributed in 980 buses, which are separated into 7 terminals. We also have 6 mechanical workshops and 1 logistical distribution center and 47 services or lines. Well, the stages of the design of an electro-terminal is like building a house, in my opinion, where the foundations are very important. And in this particular case, we have the routes, which are inside a terminal, and also the physical space available. That is very important. In addition, as part of the foundations, we have the sizing of buses and chargers. The pillars of this building or construction would be the design of use and the road safety of the terminal, design and execution, civil and electrical works. We also have the use of technology and data management software, and all of this supports or underpins the fleet operation. I will talk about from the perspective of the bus and charger sizing, since the routes and the other topics have already been discussed. I will talk about from the perspective to size buses and chargers. One needs to know, first and foremost, if you're going to do it with buses of 10, 12, or 80 meters, articulated buses, whether these are going to be buses with DC or AC connectors. You need to know the nominal capacity of the batteries, such as 80 kilowatts hour or 385. We also need to know whether they're going to use a rapid or slow